So, Assalamu alaikum, Bismillahirrahmanirrahim. We will start now our today lecture, the last lecture after this is for the course. Okay, and next week we will have exam. So, last lecture is about today. What we will discuss? We will discuss today parallel ADC. This we also call it FLASH ADC, Flash Analog to Digital Converter. Okay, in the previous classes, again, let me just go through, give an overview what we have discussed till now in the previous classes. So, guys, we have discussed first of all, we have discussed the digital ramp ADC. Okay, in detail, and what we have seen, this is the circuit for digital ramp ADC. Okay, then what is the disadvantage of digital ramp ADC? It counts each step 0 0 0 0 0 0 0 1 0 0 1 0 and so on. Therefore, this is one of the reason that the speed is slow. Okay, so we have seen that the conversion time is more, speed is slow. Okay, all these things. Then we see the error, quantization error, and why this error is coming we discuss in detail. Okay, that it does not stop at the precise value. The problem is that always we have a difference. That difference come because of the step size. For example, in this example we have seen that it is jumping from 4.5 to 5. So from 4.5 onwards to 5 will have the same answer. Okay, 1010. So these are the kind of thing that we discuss, and this error is coming because of the step size. Okay, so this is the quantization error that we have seen, and then we discuss about the conversion time. Okay, about the conversion time, the calculation of the conversion time, all these things. The disadvantage we discuss in detail. Okay, the disadvantage, as I say, conversion time will be more, and this is the formula for the full scale. If you are the maximum conversion time, what will be the maximum? The maximum conversion time, it will go up to 1 will be the full scale, right? You will have full scale value. So at that time the conversion time will be the highest. How we find conversion time? We are given this frequency. We find time of one cycle. Okay, from the frequency 1 over t. Okay, we find it 1 over t, and then we multiply with the clock cycle. If it is full scale, it is very simple. Full scale means the last step. Therefore, we have the formula for the full scale. Okay, or maximum is 2 to the power n minus 1 times t. Why 2 to the power n minus 1? I discussed with you. It is 4, but it is 15, right? 2 to the power n is 16 minus 1. Okay, 2 to the power 4 minus 1 is 16 minus 1. If it is 4 bit, if it is 8 bit, 2 to the power 8 minus 1, 255 times t. Okay. Now, since it goes through each step, so this is the disadvantage. Then we see another method, which is successive approximation method. Okay, what are the things that we have seen in successive approximation method? I told you guys this is not the part. Okay, no need to see and study. This is, we discuss in detail how it works. Is the flowchart diagram. Okay, and we discuss this one. So what it happens? We know it start from the MSB from the left hand, and it goes up to the LSB. It change each position, and it calculates the value, and if it is less it keeps, and if it is more it discards. So for example, here VA is 10.4 volt. Okay, in this example VA is 10.4 volt. Okay, so when it makes it MSB1, it calculates 8, so it will keep this value, means this one is fixed now. Then it will move to the second position, next position. Okay, 1 1. Okay, so next position is 1 here. Okay, so 1100 is what? 12, because its step size is 1, so 12 times 1 will be 12 volt. This becomes more than 10.4. 12 is more than 10.4. Discard means what? It will go back to 0. Clear? It is go back from 1 to 0. Okay, 1 to 0. So now we fixed how many position? We fixed 2 positions here. Okay, we fixed 2 position now. So we have 1 0 0 0. Then we will make third position. Okay, third position we make it 1 1 1 1 0 1 0. It becomes 10 volt. 10 is less than 10.4, so we will keep it. Okay, and then we have make the last bit, which is LSB. We make it 1. Okay, so 1011, it becomes 11 volt because it is step size is 1, and this 11 is more than that, so it is discard. Okay, and this way process is complete. So here it goes from LMSB to LSB. Okay, MSB to LSB, and it checks, and then it keeps and it discards. I discuss again because some students, last week we have very few students. Okay, therefore I discuss again. You can go through again my lecture and it will be very clear. Okay, so we find it, and always we keep the, here there is a difference. Okay, I discuss with you the difference in the digital RAM. We always go to the higher value. In SAC we always keep to the lower end. So it is 10.4, I will accept 10. If it is 12, I will discard. Okay, but in the other case we go up to more, right? Okay, and then we have other thing which is here is the timing diagram. So timing diagram, very simple. We keep the cycles here on the x-axis and these values on the y-axis, and we just draw. Okay, we take different values and we draw. Okay, very simple. Okay, so this is the way. Now you should know that I cannot give you to draw timing diagram. Okay, because our questions will be, and I'm giving you a tip now. Okay, for the exam. So I cannot give you to draw the timing diagram, but I will ask you many small questions. So you should understand what questions I am asking. Okay, so because it is a multiple choice question. Okay, so you should be able to understand the idea. Okay, so this one is, and then we see the conversion time because it is number of bits only. Why? Because we just check the bits from MSB to LSB. We just check the bits, so it is number of bits, n times t, n times t. Okay, it is always constant, n times t. Okay, then this is the example we discussed last week, that we have 8-bit SAC, and 20 millivolt is the resolution, means step size, and 2.17. Then we did very simple. We will divide it. 2.17 over 20 millivolt. It becomes 108.5. Now I tell you, if it is what you call it, SAC. So therefore, I will take, it is 108.5. So I will take 108. Okay, and I will convert it into a binary. And if it is digital RAM, I will go to the higher value. Clear? I will keep the 109. Okay, so since it's SAC, we keep 108. If it is digital RAM, I will keep 109. Okay, everyone, clear? Okay, so I give the whole, and then there is a comparison here for the timing for the maximum timing. So we know the formula, very simple. Okay, 2 to the power n minus 1, and it is simply the number of bits, and we can just find it out. Okay, it is so simple. Okay, now we come to the today lecture. What we will discuss today is parallel ADC, flash ADC. This is the third analog to digital converter. The third analog to digital converter, we call it flash ADC. Okay, first of all, this is the fastest. Okay, flash, then from the name you can see flash ADC. It is fastest. Why? You have the input, the analog input from here. This is the input, and you get the output directly in one step. Input, allow to output. Clear? Input and output. Very simple. One step. There is no like a table, conversion table, this kind of things. Okay, we directly find input alatul output. Okay, what is the how so what is the timing, this what is the this one conversion time is up to 15 nanoseconds, 50 nanosecond, and this conversion time is limited because of the gates, this gates. Okay, that we have here, the resistors and this buffer. Okay, that we have the comparator and the sorry, comparator, this comparator. Okay, and priority, I will discuss with you, don't worry about this one. Okay, so within this, since we have a circuit, so there will be a time delay. Okay, because there is a propagation delay when the signal the signal will go input. Okay, we will have an input here and we will have an output here, so it will take some time. because the signal will propagate inside the circuit, so there will be a propagation delay. Okay, so that one is the only delay, otherwise there is no such conversion time. Okay, so usually the conversion time is very low. You can see it is up to only 50 nanoseconds, so it is the fastest. Clear, everybody? Now we have to understand how does it work. Okay, so first of all, you need to understand what are the parameters that we have here. First of all, we have three parameters here. Number one is the resistors. Number two, we have comparators. Okay, and number three, we have priority encoder. Okay, priority encoder. So I will discuss now each step one by one. Okay, comparator, everybody knows well. We have seen the comparator before also. Okay, we have negative and positive. So it's very simple. If it is this one positive is more than the negative, it will be 1 here. If negative is more than positive, it will be 0 here. Okay, now in the negative side, if you see the negative terminal, what is coming? Negative terminal, we have the input. Okay, input, and here we have one. No problem, go to. And here we have, okay, this sorry, this moment. Here we have these are this signal coming from here. Okay, I will discuss what will come here. Okay, so we have at the negative, we have the input. Okay, our analog input, and we have one voltage here. It will compare. Okay, if the input from here is more, okay, and this input is less, it will give you 0 because it is going to negative. Okay, if it is less, this one is less, this one is more, plus is more, negative is more, because this one is going to the negative terminal. Okay, so it will be 1. Okay, if this one is what we call it more, and this is less, it will be 0. Okay, we know if it is plus is more, minus terminal is less, then it will be 1. If minus terminal is more and negative terminal is more and positive terminal is less, it will be 0. Okay, this is the comparator, simple comparator. First thing. Second thing, how we determine the voltages here. This is very critical, and you have to understand what is the, yes, I'm coming to you. How you can calculate the voltage here? It is very simple. Okay, what you do first, it is like a voltage divider rule. Okay, we all know voltage divider, right? Okay, so for example, if I tell you what is the voltage here, okay, what is the voltage here? Very simple. What is the voltage here? We have, how much is the voltage? It is uh, this one 10 volt, right? Okay, 10 volt here, and we have 3 kilo ohm, 1 3 4 5 6 7 8 9. Okay, sorry, 3 4 5 6 7 8, 3 kilo ohm, 4 kilo ohm, 5 6 7 8 9 10 kilo ohm. Okay, so it means if I tell you, very simple, if I apply voltage divider rule, what is the voltage here? Here this resistance is how much? 1 kilo. This resistance is 1 kilo. Okay, no, I'm not 9 kilo. On the top we have 3 kilo. Okay, and then we have total. See, now count the number of resistors. 1 2 3 4 5 6. Okay, sorry, 3 4 5 6 7 8 9 10 kilo. Clear, everybody? Can you see? Everyone, can you see? Yeah, it has 1 kilo. Okay, sorry, this is not written. It is also 1 kilo. This one is also 1 kilo. Okay, write down in your handout. Okay, it is also 1 kilo. Okay, so what we have now, if I ask you what is the value of the voltage here, if I ask you what is the voltage value here at this point, how you will find? Very simple. we will apply the voltage divider rule. What is the voltage divider rule? Voltage divider rule says that what is the resistance here, this one divided by total resistance. So here it is 1 kilo over total resistance is what, 10 kilo, right? Times 10 volt is the total, because here we have 10 volt. Clear? This is 10 volt. So how much you got? 1 volt. Yes. Okay, 1 volt. Clear, everybody? So here we have, at this point I get 1 volt at this point. Okay, what about this point? How much what will I get from here to here? At this point it will see how many resistors? 2 resistors, right? So therefore we have 2 kilo over 10 kilo times total voltage is how much? 10 volt, right? So how much I got? 2 volt. Is it okay, guys? Is it clear? Everyone okay? Now please, others, everyone okay, right? If I ask you what is the value here at this point, what you will do, very simple, you will find out how many resistors you have. 1 2 3 4 5, because it will see from here up to the ground 5. Okay, so 5 kilo over total is 10 kilo, because this last one is 3 kilo. Okay, times 10 kilo. Okay, 10 volt, sorry. Okay, so you got how much? 5 volt. Okay, so in this way I will simply find out all. Here the first one is 1, then 2 volt, then 3 volt, 4 5 6 7, and then we have here 3 kilo ohm, right? The last one is 3 kilo ohm, so therefore it is 10. Okay, because here you will have a 3 voltage drop. Clear? So we find out. Okay, we find out each positive terminal. Okay, so what we know now, very simple, we know first of all the positive terminal, and we know also what is the input. Clear? Okay, what is the terminal, positive terminal, each one of them, and we have total how many comparators we have 1 2 3 4 5 6 7. Okay, 7 comparators. Okay, what will happen now, guys? Okay, this comparator output before the bubble. Okay, don't look the bubble. Okay, before the bubble. Okay, this is the comparator output which we have here. Okay, so this comparator output we have, the first one is C1, C2, C3, C4, C5, C6, C7. Okay, so I will simply find out the values. Clear? I will simply find out the values. So now we have, the first step is what? This is my input VA. I will consider different values of the input, and I will check what will be the comparator. Comparator will depend. Now these values are fixed. Okay, this is fixed. How I fix? Why it is fixed? Because the resistance I will not change. Once given resistance, it depends upon the resistance and the total voltage here. Okay, so they will not change. They will not change. Okay, based on that one, total voltage here and the resistance, I will simply find out all the positive terminal. Okay, and they will be fixed. They will not change now. So we have 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt. Okay, and then finally we have 3 kilo ohm resistor, so 10 volt. Habibi, look here. At this point, how many resistor you will consider? You will consider only one resistor, because below the point only one. Okay, but so therefore we have 1 over total resistor, how many? 10 kilo times how much voltage? 10 volt. Clear? But for example, if I tell you at this point, please now listen to me, at this point. Okay, how many resistors below this point? Okay, because it is this one will be from up to ground. Okay, we consider up to ground. So how many up to ground? How many resistor we have? 2 resistor, right? Each one is 1 kilo, so total is many? From there to there, 2 kilo, right? Over how much total resistor in this one is 10 kilo times total voltage. What is the total voltage available? 10 volt. Okay, so how much I got? 2 volt. Simple. Clear? Okay, now Anas. So my point is very simple. First of all, you see the total voltage, you see the resistors, and you find all these positive terminals. This is the first step you should do, okay, by closing your eyes. Okay, very simple. You will apply voltage divider rule and you will find it. Okay. Then based on the input, okay, you will given the input and you know the comparator. I told you how comparator works. If plus is more, okay, and we are considering comparator output, okay, here, okay, before the bubble, okay, don't look the bubble now, okay, before the bubble. So we consider we will find the terminal, this comparator output is very simple. If plus for the comparator, how is the output? Comparator is very simple. How it works? If plus voltage, okay, V plus is more than V or voltage at the negative terminal, okay, what will happen? Comparator output will be what? Output equals to 1, okay, and if voltage at negative terminal will be more than voltage at positive terminal, comparator output equals to 0. Clear? This formula I will keep and I will now I will show you the table. So what happened now? Look this table. What I did, I consider this table, okay? I'm talking about this table, okay? What I did, I consider different possible inputs, okay? Different possible inputs and what will be the comparator output, okay? Different possible inputs and what will be the comparator output. Clear? So here I say the first input. Now look only the first input, 0 to the first one, 0 to 1. 0 to 1 means less than 1. 0 to less than 1, okay, means 0.99999 whatever, less than 1, okay. What will happen now? So 0 to less than 1, any value like 0.2, 0.3, 0.4, 0.5, whatever, okay. What will happen? Assume I have the input here is 0.9 or 0.8. From 0 to 1, any value less than 1, okay, any value 0 to 1. What will happen now? Now here it is 1 volt, right? Here it is 2, 3, 4, okay, all of them. All the positive terminals are more than negative terminal, right? Clear, everyone? So therefore, all the comparator output will be what? 1. Is it okay? Everybody understand? Do you understand the comparator output, guys, for this example? If the input is 0 to 1. Okay. Again, let's see again. I have input only the first in the table, okay? Any input from 0 to less than 1, any input from 0 to, because it is analog to digital converter, so analog input, right? Any analog input up to less than 1. Less than 1 means what? It can be 0 0.2, 0 0.3, 0 0.4, 0 0.5, 0 0.6, whatever, okay? What will happen now in our case, in this example? So this input, again, please, this is very critical to understand, okay? This input is from 0 to less than 1, means it can be up to 0.9999, whatever, okay? My question is simple, that what will be this comparator values, okay? This comparator value, for example, the first comparator, okay? You have, let's say, 0.9. Here you have 0.9, okay? This negative terminal is 0.9 and the positive is how much? 1, right? So you have 1, and here a point, here this is the input, okay? This is our input, which is coming here, this one, this, okay? Negative terminal, okay? So, because this one is going to the negative terminal, input is going to the negative terminal. So since positive terminal in all cases, all the positive terminal will be more than the negative terminal, because our input is at negative and it is less than 1, right? So all positive terminals, this one, all positive terminal will be more than the input, okay, which is less than 1. So all the comparator output will be 1. This is the reason I see here all 1. Is it fine now, everybody? All of you understand this point? Everyone, please. Okay. Let's see now. Second example. Okay. Let's see second one. Now, I consider the second type of input. Assume that I have the input from 1 to 2. 1 to 2 means any value which is from 1 up to less than 2. Less than 2 means it can be 0.1, 0.9999, or it can be 1.2 or 1.3, any value, okay, any input, okay, any input from 1 to less than 2, okay. What will happen now? What will happen now? So this is, let's say 1 to less than 2, let's say it is 1.7 volt. I am considering any value 1.7, okay. This is 1.7. So this, I am considering the first one. So this one, this is going to this negative terminal, so it is 1.7, but the positive is how much? 1, right? Now negative is more than positive, right? Negative is more than positive, so this one will become what? 0. Yes, very good, 0. So therefore, if you see here, this one is 0. C1 is 0. Clear? Clear? What about C1? This one, C1 is 0. What about C2 now? Go back again. So here I assume 1.7. I assume 1.7. Okay. Okay, because it is up to, I say the my input is 1 to less than 2, okay, 1.7. So this negative terminal of I'm taking on second this one, okay, so it is 1.7, okay, okay, but the positive is how much? Positive is how much here? 2 volt, right? 2 volt. So this positive is 2, negative is 1.7, so the output here will be how much? 1. Clear? So therefore you see here in this one is 1. Similarly, all of them will be 1. Why all of them will be 1? Why? Because in all cases, either I come here in the C3, C3 again the same thing, right? It is how much? 1 to 3 volt. This is 3 volt. 3 volt is more than 1.7. 4 volt is more than 1.7. Similarly here 7 volt, right? So 7 volt also more than 1.7. So in all cases, since this input is, yes, very good, 1.7, so up to, so all of them are less, so khalas. So what is the conclusion? We have this one is 0, others all are 1. Now let's see 6 to 7 volt. 6 to 7, what will happen? 6 to 7, assume I have 6 to 7 means assume I am assuming a value, I'm using 6.678 volt is my input, okay, analog input. So I have, go back, so my input is how much? This my input is how much? I write here 6.678, okay, so I write here that my input is, right, anyways, my input is how much? 6.678. What will happen now? Tell me what will happen now. If you see now, this is here, the positive terminal is 1, this terminal is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So this is how much? 6.678. Now this in this case, negative terminal is more than 1, so it is 0. This one also what? 0. This one also what? 0. Am I right or not? Okay. Except this one. Very good. Except because here it is 7 and here our value is 6.78. So only this one will be 1 and others all 0. Is it okay, everyone? Everyone tell me. Is it okay? Now see the last case. Now it is telling you any value which is more than 7. More than 7 means 7.2, 7.3, 7.4, 7.5, up 8.5, 8.3, 8.2, 9.1, up to 10. Why up to 10? Because we cannot cross more than 10. You know why? Because our supply is here 10. Okay? Up to 10. Okay? Maybe 10. Yes. Okay, up to 10. We can go up to 10. What will happen then? What will happen then? If so, I have assume I have 9 point greater than 7, right? Any value greater than 7. Okay, let's say I assume 9.6. Okay, or I assume 7.8. Any value. Okay, any one of them. Now what will happen? All the inputs are what? The maximum input is what? 7, right? Okay, so the negative terminal, this value will be more than all of them. So therefore, all of them, all this comparator will give you how much? What if they will give you? All 0, right or not? Clear? All comparator output will be 0. So the second step, how to find the comparator output. How to find the comparator output. Up to this one we know. We have done this part. Okay. So very simple. I am telling again, first of all, how will you start? You will see total voltage, you will see the total resistance, you will find the voltage at each terminal, and be careful what is given to you. Okay, so you will find out the voltage at each terminal, and after that you will see your input, and depending upon this one, you will find the comparator outputs. Clear, everybody? Now the last step. Okay, I find out the comparator output. Now the last step is, depending upon the comparator output, what will be my digital output. Okay, because eventually I have input, analog input, and I have to find the digital output. And for this digital output, it will depend now this periodicity comparator. Okay, this one, sorry, this here we have periodicity encoder. Okay, we have this periodicity encoder. We have here. Okay, so we have this clear. We have this periodicity encoder. Okay, so now how it depends, periodic encoder. Okay, how it depends, the output depend upon the periodic encoder. Now understand very carefully. Okay guys, very carefully, I will discuss with you something. First of all, you should know this periodic encoder, it has the input from all the comparator, but all the inputs are bubbled. Can you see guys? There's a bubble, right? Okay, and I have to find out the output. Okay, so how these are all bubbled. Okay, everyone, can you see guys? Can you see? Okay, so not 0, I mean bubble means what? If the comparator output is 0, it is become 1. If it is 1, it will become 0. Clear? The input, we will see collectively how does it work. Okay, so what will happen now? So we have this priority encoder. Okay, all the comparator output are coming to this priority encoder with a bubble. Okay, so how will you write the output depending upon the comparator? Very simple. Assume assume the second case. We will see for second case, then I will see the first case. Okay, very simple. You start from the right side, C7, C6 that you have find, and you see where is the first zero. So first zero is here, right? This is the zero. So again, I start from the right side, and I go from right to left, and I see where is the first zero. I am discussing the second case first, okay? 1 to 2 volt, okay? The input is 1 to 2 volt. So I see this one is the first zero, right? What is that? When that zero is for which comparator output? C1. And what is 1? What is 1? This is 0, 0, 1. Very simple. Again, for example, you are looking for 5 to 6, okay? What you will go do, you find all the comparators. As I said, you will go from right to left, and you will find which is the first zero. So in this, if I talk about this input 5 to 6, 5 to 6, where is the first zero? The first zero is which one? C5, right? C5. What is 5? What is 5? 101. So simple. Is it okay, guys? Is it okay? For example, I see the 0 to 7, 6 to 7, the last 6 to, okay, last one. Okay, last one. Greater than 7. I found all comparator output 0, 0, 0, 0. I will go from right to left. I will see which one is the first. So the first one is the first one because all of the output was 0, right? So 0 is the first one, which is C7. So will become 1, 1, 1. It is so simple. Okay, and why it is happening like this? Why it is depending upon 0? Because of the bubble input that we have here. Okay, because of the bubble. Now, what about the first one? First one. In the first one, when it goes from right to left, 1 minute, guys, 1 minute, please, just listen to me what I am teaching you. Okay, please don't go here and there. Okay, please focus. Okay, so the first case now, please, the first case. I will come to that point. Okay, how many comparator? The first case. The first case 0 to 1. You go from right to left. Do you see any zero? Do you see, guys, any zero? No zero, right? No zero. So therefore it is 0, 0, 0. Okay. So but second one is C1, so 0, 0, 1. Then C2, so 0, 0, 1, 0. Okay, and so on. Okay. So this is the way we simply find the output. Is it okay? Everything is okay? Do you understand how does it work? Everybody? Okay. Now the question. Now the question was one student was asking me that teacher, how many number of comparator? It is very simple formula. You can see here. Number of comparator is what? 2 to the power n minus 1. Number of resistor is what? 2 to the power n. Okay. You can see how many comparators we have. 7 comparators, right? Okay. Why? Because we have how many bits? 3 bits, 7 comparators. Okay. And how many resistors we had here? In this example, how many resistors we have? 1, 2, 3, 4, 5, 6, 7, 8 resistors. Clear? So 8 resistors, 7 comparators. Okay, why? Because of this formula. Is it okay? Okay, everyone? Everyone okay? Okay, भाई साहब, कुल्लू नफर quiz. Okay. Now listen. Everybody solve this question. Okay. Now please, everybody. No, not possible. In this example, not possible. Okay. Now everybody will solve this question. Okay. This question I will just discuss with you, as we have seen that how many bit output we have? 2-bit output, right? So how many comparator we have? 3. And how many resistor we have? 4. Because 2 to the power 2 is what? 4. And 2 to the power 2 minus 1 means 3 comparators. Okay. Please, everybody look this example and solve this output. Okay. So what is in this example we have here actually? That we have, this is the 15 volt. Okay, and all these resistors are how much? We have the value 10 kilo, 10 kilo, 10 kilo, in the last one is 10 kilo means, okay, so 10, 10, 10, 10, okay, total is 40 and each one is 10, okay, means this total voltage, I'm just giving you a hint, this total voltage 15 will be divided by 4, right? Okay, 4, and you will find here and so on, okay, and the same method I have got done, okay, and then what you will do, you will find the comparator output, and then you have the priority encoder, and then you will find the output. I need this output and this comparator, okay. What are our inputs? Now here we don't have a range of the input like previous example. Here we are distinct input. Now this is the way the exam questions will come, okay. So we have distinct input, how much? 3.5, 4, 12, okay. So please everyone solve it. Please solve everyone, okay. I'm just going to drink water. Everybody solve it, then I will discuss. Okay, guys. Everyone solve? Yes, I think this is answer. Right, 1 1 0 1 0 0. Everyone solve, everybody? Okay, very good. Okay, so very simple. Let me discuss here, everyone. I hope everyone has solved. Just let me discuss. It is so simple. So we have what? 15 volt. Okay. So first of all, you will do what? 15 by 4, right? Okay, because we have total 4. Okay, very simple. We know that 4. So 15 by 4 will be how much? I think 3 point, how much? 15 by 4 will be 3.75. Yes, very good. Okay, 3.75. So here it is so simple. You know how much what will be the voltage? Here you will have 3.75. Here 7.5, and here 11.25, right? So 3.75, and then the double on the next will become 7.5, and then you will add 3.75 more, because we know it is like this. Okay, and you can apply voltage divider rule, or this method is very simple. Okay, because all of the voltage resistors are equal. Okay, so we have I think 7.5 plus 3.5, so we have 11 point, how much? 25, right? Okay, I guess, yes. Okay, and then 15. Then very simple. Okay, so you have this one, you find it, and now this is the value. So it is let's say 3.5. If it is 3.5 here, or this 3.5, this one, if you have 3.5 here, what will happen? 3.5, and it is what? 3.75. Okay, so plus all is more than this one, so you will get 1 1 1, right? All of them 1 1 1 1, so you got output how much? 0 0, right? Okay, very simple. And next, for example, this case 12 volt. So you have 12 here, the input is 12. How much are the values here? It is 3.75, it is 7.5, it is 11.25. All these values are less than 12, right? So this is the reason that all of them is how much? 0, right? Because negative is higher than everyone. So the output will be how much? 1 1. Clear? Because it is purity into encoder with bubbled. Is it okay, guys? Everybody understood? Okay. Any question, anyone, please ask me. Please ask me. Abdullah Faris, okay. Abdullah Taisar, okay. Ahmad, okay. Ammar, Faisal Ghatani, Faisal Baba, Anta sleeping or watching some movie. Hamad, Saeed, okay. And Hassan Al Musa, Khalaf, Khalid, Kumail Bhai, sure he is watching some movie on the mobile. Mahdi, Mahdi Ali, okay, Muhammad Al Intif, Muhammad, Muhammad Bu, okay, and this Mohsin, Murtaza, Mustafa, Raja, Raja Bhai, Anta Majood, Mapi. Lunch time finish already, it's lunch time. 4 o'clock now. Raja, Salim, Salim and Raja. Where are they? Salim here. Raja. See, Raja. See. Raja, what he is doing. He is online, but I think he is watching some movie on mobile. Okay. So some students, mashallah, they appear online, but alhamdulillah, they are not with me. They just make themselves inside the room, and then they do something. Raja Kamal Hain. Raja, ana malum. Ishanta Shuhal. Okay. Okay, guys. Anyways, Allah, ya akhi, your name is not appearing, ya akhi. 381901001. Mushkila. I cannot call your name as ID. Anyways, guys, now we have the last topic, okay? Last topic, inshallah, for the course, sample and hold circuit. Sample and hold circuit is very simple. SH, sample and hold circuit. Yes, if we have the positive terminal same as a negative, what will be the result? Yes, very good question, by the way. Okay, this question is very good, and understand. Okay, if it is same, also will be zero. Clear? If it is same, only if it is more. Very good question, by the way. No, not extra resistor. Okay, this is the way, because this is the not the extra resistor. Okay, this is the format, because you have, it's not extra. We have three comparators, so one must be here. Resistor must be here, then here, then here, then here. One must be here. We cannot just keep any voltage here like this. Okay, this is the way we do. This is the first thing. Second thing, the other question is very important. Okay, the other question is telling you if both positive and negative terminal of the comparator are same, what will happen? It will, output will be zero. Okay, the output will be one only if positive is greater than negative. Okay, if it is equal, or if positive is equal or to negative, output will be what? Zero. Okay, remember. Okay, or if positive is less than negative is clear, but if the equal also zero. Clear, everyone? It's a very good question. Now the next topic is sample and hold. Sample and hold is very simple. Okay, let me just you can go through the discussion and I will just discuss here. I think you guys have studied before. Okay, I hope that you studied before, but just only I will discuss with you here. What is the purpose of the sample and hold? Sample and hold is like, understand this way. You have a ADC, okay, analog digital converter. Okay, now we all know that analog digital converter, it takes some time, right? Okay, to convert from analog to digital. Okay, so therefore, if for example one input is there, okay, we have this one, like when we go to any shop or any place, we make a queue, right? At first, and then second, then third, then fourth, and nowadays due to corona we have also the distance. Okay, we maintain the distance as well. Okay, so the same idea means, if you are in panda shop, the person the person who is on the counter, he cannot handle two people at the same time, right? He will finish the first, then second, then third, then fourth, and so on, right? So the same idea, what happened now here, that you have the input, okay, from here. Okay, and then this input, it will take some time, it will go to the ADC, it will take some time to take the conversion, right? So this one, what we control, okay, by sample and hold. Sample means the input it passed through, and then hold means it takes some time, as per the conversion time, it takes some time to convert. At that time, this but this one, it is like a door here. Okay, this one is like a door. Okay, so once one input is inside here, this door will be open. This will be open circuit, means not other input can go inside, right? Okay, once this input will be converted, okay, it will finish conversion, then it will open, it will close again, and another input will come. This is called sample and hold. Sample and hold. Okay, sample and hold. So this one, we have here. Yeah, again, very simple, no problem. Okay, that like if our analog to digital converter, okay, it is going to analog to digital converter. If our analog to digital converter is converting one analog input to digital, shall I send another input also? No, right? Because there is a conversion time. It will take some time to convert, right? So I should send in the queue. Means the first input will go, it will convert, then second input will go, it will convert, then third input will go, it will convert, right? Like I give you the example of the shopkeeper, okay, all the counter, okay, in the panda. You can counter up the person who is on the panda counter, okay, the he cannot handle two at the same time, two customer, right? He will finish the first one, the other will be waiting in the queue. Same idea here, okay. So I send one input, analog input, okay. That analog input will pass through this buffer, okay. And this is the capacitor here. So capacitor will hold the input, okay, for that particular time, and then this input will go to the ADC, okay. And then this switch will be open switch, open circuit. Why open circuit? Means no other input can go inside, okay, unless it has finished converting this input. When this input will be finished, okay, conversion, then this one will be closed again, and then the next input will go here. Then it will be, capacitor will charge, means it will hold it for some time. It will go to the ADC, it will be converted, and again it will be open, okay. So there no other input can go. This is called sample and hold, okay. So it samples the analog input, then it hold unless it is converted, and it doesn't allow any other input to go. Once that input is finished, digital input, analog input is finished to be converted into digital, then the other analog input will go. Clear, everybody? Okay, so very simple. And why we have this resistor here? So we have a this one control, what do you call it, control switch here, okay, to control this one, like a gate, okay, gate, like a gate to enter, for the input to enter. And then we have a capacitor for the holding, okay. Whatever the input will go, we input data analog input will go to the ADC will be going. It will hold it for some time so that ADC can change it. Yes, capacitor. ADC will be held by capacitor. Okay, capacitor will charging and discharging, so it will hold it unless it is completely converted into the analog, from analog to digital. Clear? Clear, everyone? Okay, so it is the simple operation for analog to digital converter. Okay, so now let me just read this one, and it will be clear now to you. So when an analog, so I'm reading here, by the way, guys, please, we will read this point, and so if there's any question you can ask me. When analog voltage is connected directly to the input of the ADC, the conversion process can adversely affect if the analog voltage is changing during the conversion time. Means one analog input is there, okay, one analog input is there and converting, and you send another analog input. It doesn't make sense. Before the conversion it doesn't make sense, right? So this is what he's saying, that it is converting, it is changing, and you send the another one, okay. The conversion process can be adversely affected if the analog input is changing during the conversion time. The stability of the conversion process can be improved by using the sample and hold circuit to hold the analog voltage constant while the A to D conversion is taking place. Okay, so because of the conversion time, we study already, it takes some time for the input, so we must hold it. Okay, we must hold it. It takes some time to convert. Figure shows a simplified diagram of sample and hold circuit. A sample and hold circuit consists of the two unity gain buffer amplifiers. So this is the buffer amplifier. Buffer. Buffer means what? It's just simply like a gate. Okay, whatever the input, the same is the output. Okay, buffer amplifier. Okay, buffer means what? It will just not affect the this one. Whatever the input, the same value will maintain. Okay, buffer amplifier. And this, if you see here, yeah, V out equals to V in, and if you see what is the gain is 1, like a buffer. Okay, gain is 1 here. So the two unity gain buffer amplifier, a capacitor, and a digitally controlled switch. A digitally controlled switch is what? To control the inputs. Okay, unless this is the digitally controlled switch we have. Okay, unless one is not converted, the other input will not go. Okay, unless it is finished conversion, then it will go. The capacitor will be connected to the input of the A1 when the digitally controlled switch is closed. This is called sample. The switch will be closed long enough for the capacitor to charge the current charge the current value of the analog input. When the switch opens, the capacitor will hold this voltage so that the output A2 will apply the voltage to the ADC. So it will take the time to go to ADC and convert it. Okay, this is what we call sample and hold circuit. Very simple. So again, it just convert. It make the operation more controlled, simpler. Okay, guys. So when we have for digitally controlled switch, when control is 1, switch closed. Switch closed, control means this input will pass through. It's called sample mode. Okay. And when the switch is 0, means open now. So means now no further input will go inside. It will take time to convert into ADC. Once it will finish, then again this switch will be 1 close, so next input will go. So 1, then 1, then 1, then 1. So in a queue, in a sequence. Clear? All the input will not go at the same time. Clear, everyone? Now the last thing is acquisition time. So the acquisition time is what if the computer controlled if in computer controlled data acquisition system, the sample hold circuit will be controlled by our digital signal from the computer. We have seen already control input 1 and 0. Okay, the computer signal will close the switch in order to charge the capacitor to a new sample of the analog voltage. The amount of time the switch would have to remain closed is the acquisition time, and it depends upon the capacitor value and the characteristics of the, so how much time it will remain. Okay, it has to, because it has to hold for some time depending upon the conversion time, right? So that is the acquisition time because it is taking some time. Clear, guys? So this is the end of our course.